What is going on, everyone? Welcome back to another episode. Today, we're actually going to be doing a CFD simulation in ANSYS in order to do the fluid flow over a cylinder. And this is going to be useful in order to see the von Karman effect and the shedding of the vortices of the fluid from the cylinder. So to be more specific, our analysis is going to be the flow of water over a circular cylinder with a 1 meter diameter. And we're going to do this simulation for one cylinder, two cylinders in tandem that are separated by 2D, 3D, and 4D. So what do I mean by this? The two cylinders in the fluid flow, their centers are going to be separated by 2 times their diameters. So in other words, it's going to be separated by 2 meters for one simulation. It's going to be separated by 3 meters for another simulation and 4 meters for a fourth simulation. And we'll go ahead and do this simulation again for 3 cylinders in tandem, again separating them by 2D, 3D, and 4D. And the objective of doing all of these simulations is to see the von Karman effect and the vortex shedding of the flow as it passes by the cylinder, and to observe how multiple cylinders in tandem, as well as their spacing, is going to change how the von Karman effect is going to look like. On screen now in the middle, you can see that these are the results that we are going to want to obtain from the one cylinder simulation. So we have the contours up here where we can evidently see the vortex starting to occur as they are shedding off the cylinder. And the solutions we're going to want to plot for are the coefficient of drag and the lift coefficient here. And all these simulations are going to be broken up into multiple videos. This first video is going to be dedicated to the one cylinder and is going to be the longest video simply because I'm going to go step by step through the details of how to set up the simulation and how to get the results that we want to attain in order to see the von Karman effect occur. All that being said, let's jump right into it. So the first thing that we're going to want to do, obviously, is load up ANSYS Workbench, and we should be greeted by this familiar screen. We'll go over here and take the fluid flow Fluent analysis system and drag that into our project schematic. We can rename the title of it to 1D cylinder, just to give a bit of description to what our CFD simulation is going to be. And finally, the first step to every simulation is setting up our geometry. So we'll go ahead and double click on geometry to launch SpaceClaim. And as you can see down here, it says starting SpaceClaim. So we'll wait for that to open. Now with SpaceClaim open, we can go ahead and build our geometry. For CFD simulations, the geometry that we want to build is the fluid domain, or the domain that is around the object, because that is what describes the behavior of the fluid. And this is different from FEA simulations where we design the geometry to be the object itself because we're interested on, say, stresses and strain on the object. So again, for CFD simulations, we want to build the geometry that is around our object. So in that case, it's going to be the fluid domain around the cylinder. So first things first is I want to sketch on the XY plane. So I'm going to end sketch because, as you can see, we're designing here on the ZX plane. So I'll end sketch. And I'll actually change my units because I think by default, it normally puts it into millimeters. So we can go to File, SpaceClaim Options. We can press on Units here. And you can change your units, whatever type you want, metric or imperial. And you can change to any type of units if you wanted to, for whatever reason, CAD in nanometers, you could do that, or centimeters, millimeters, micrometers. But for today, I'm going to be CADing in meters. So change that to meters, press OK. And now we're going to build our geometry. So we'll enter sketch mode and we'll select the plane that we want to sketch on. And we'll put it planar to that face. And now we can take the circle command in order to build the cylinder of which the flow is going to go around. And we can dimension the cylinder to have a 1 meter diameter, like so. And we can zoom out. There we go. And next, we're going to build the actual fluid domain. So we can go ahead and choose our rectangle command and build a rectangle around this cylinder. And we are going to dimension the inlet length to be 5 times the diameter. So we'll change this to 5 meters. And we will dimension the outlet length, or the length from the center of the cylinder to the outlet, to be 15 times the diameter. And the reason why I'm giving these 2 dimensions as so is because we are interested in seeing the von Karman effect after the cylinder. So before the cylinder, we're going to have a uniform flow because we're specifying the inlet velocity of the flow, and nothing is in the way of the fluid. So it's going to be a uniform flow. Whereas we are interested to see what's going to happen after it interacts with this body here that is in the middle of the flow. So this is why we make the outlet length longer, in order to see how the fluid will behave after its interaction with the cylinder here. We're also going to make the width of this fluid domain a little larger. So we can dimension this to the center, like so, and we'll give this a 5 times diameter as well. And we'll do the same for the bottom. That way, the walls of the fluid domain, because the top and bottom, this top and this bottom, are going to behave as walls of the fluid domain. And so we don't want those interacting with or interfering with the flow that is happening at the cylinder here, at the interaction of the fluid and the cylinder. So this is our fluid domain. We can go ahead and exit, return to 3D mode, or at end sketching mode, either or. So we'll press on this button here. And so this gave us 2 surfaces. What we're going to want to do is delete this surface here. So select the cylinder surface and delete it. And again, we do this because we're interested in the fluid domain and not the object domain for CFD simulations. And this is our built fluid domain. So now we can move on to the meshing stage of our simulation. So we'll go ahead and quit SpaceClaim, and we'll go back to the ANSYS workbench, and we'll launch the mesher. Double click, and you can see here it says starting mesher. So I will be back once that's launched. Now with the mesher loaded, we should be greeted by a screen that looks like this. We can go ahead and press on the Z-axis here to make it planar. And we are just going to right click and generate a mesh and see what mesh ANSYS built for us. That was pretty quick, and we can see that is pretty coarse. We are going to have to refine this quite a bit. So the first thing that we're going to do is we're going to right click on mesh and insert a sizing. As you can see here, the yellow elements are the inputs that ANSYS is waiting us to specify. So it wants us to specify the geometry and what type of element we want to specify, whether that be the size, the number of divisions, the sphere of influence, body influence, and factor of global size. For this mesh, what we're going to do is we are going to specify the element size. And we are going to choose the edge selector tool in order to choose the cylinder edge here and apply that to the sizing. So now we can see that the edge has been applied to the sizing. And what we're going to want to do now is specify the size of the elements that we want. So I'm going to specify them as 0.025 meters. Oop, there we go. And now we can update the mesh. Now we can see that the mesh around the cylinder is a lot more refined, which is good because we'll be able to more accurately depict how the fluid behaves during the interaction between the uniform flow and the cylinder wall. Though the rest of the domain is pretty coarse, so we can refine that as well. We'll click on mesh again, and we'll insert another sizing. And this time we'll choose the face selector tool and choose the fluid domain face, press apply. And we're going to specify the element size here to be 0.1. And we'll go ahead and update this. So yeah, that took a second to mesh, but now we can see that our mesh is a lot more refined and quite orthogonal, I should say, in the fluid domain. So that should help us a lot and make the calculations be fairly simple for the solver. There are a few instances where it had to readjust, but that is pretty okay. Now we are going to want to make the fluid domain around the cylinder a lot more orthogonal. And so in order to do this, we can insert in inflation. So we'll right click on mesh, go to insert, and press on inflation. So here it's asking us for two things, the scoping method. So what is our geometry? And it's asking for the boundary. So for the geometry, we are going to press on the face selector tool and choose the fluid domain, press apply. And now for a boundary, we're going to select the edge selector tool, select the edge of the cylinder, and apply that to where it says no selection, left click on that, press apply. So now we have our inflation applied to the fluid domain, to the face of the fluid domain with the boundary of the cylinder here. And we're going to change the inflation option to make it a first layer thickness. So we're going to want to define what the thickness of the first layer is, and we are going to put the same thickness that we specified the edge sizing to be in order to make it orthogonal. So we're going to specify that to be 0.025, and we're going to put 20 layers of inflation at an inflation rate of 1.5. So now our inflation is applied, all the variables are put into place, so we can go ahead and update our mesh. Now with our newly generated mesh, we can see that the inflation made the mesh around the cylinder wall a lot more orthogonal, which will be better in order to capture the details of the fluid behavior as it interacts with the cylinder wall, and just to make the overall computational analysis easier for the computer. So now what we can do is specify a couple of domains so that Fluent knows how to apply properly the boundary conditions to our fluid domain. And what do I mean by specifying domains? I mean specifying that these are going to behave as walls, and the side here is going to behave as an inlet, outlet, and again, cylinder wall here. That is what I mean. So in order to do that, we'll select on the edge selector tool. We'll select this edge here, right click, and create name selection. We want to press on create name selection. And we'll name this inlet, because this is where the flow is going to be coming into our, you can view this as a tube or a pipe. It's good. The fluid is going to be entering by the inlet here. So we'll name this as the inlet, and we'll do the same here. Select this edge, create name selection, and name this the outlet. Now for the walls of the domain, you can go ahead and press on the edge here, and you can control and hit the other edge here in order to select both edges. And we can go ahead and create a name selection for the wall of the fluid domain. I will just name this wall. And we'll also want to specify the wall of the cylinder. So I will go ahead and edge select the cylinder edge here, create name selection, and I'm going to name this cylinder. That way I know that this is the cylinder, the wall of the cylinder. Press OK. And now you can see the name selections in the tree appear here: inlet, outlet, wall, and cylinder. And you can verify them by clicking on them. It will specify the inlet, the outlet over here, the walls, and the cylinder wall. So now with our name selections in place and our mesh created, we can go ahead and specify the boundary conditions in Fluent in order to run the simulation. So we're going to exit the mesher by clicking on the big X. And we are going to, you can see here that we have a lightning bolt here. So this is requiring us to update this part of the simulation. So we'll right click on this and press on update. And this is just making sure that we send all the information from the mesher into the setup of the program. And once that is finished, you will see that we have a check mark appear beside mesh, meaning that all the information from mesh has gone into the setup of the simulation. There you go. So now we will double click on setup, and this will start up Fluent, as you can see down here. So we'll wait for that to load. As you can see, we are met with the Fluent launcher now, and there's a couple things that we need to specify before opening the actual Fluent program. The first thing is our dimensions. Now, by default, ANSYS knows that we're dealing with planar objects, so it knows that the simulation is going to be a 2D simulation. We can go ahead and click on double precision for this simulation. And for my computer, I know I can up the solver processes to 2 and the GPU for 1, but this is going to depend on your computer at home. So make sure you specify these values. And we can go ahead and press on start to launch the program. Now with Fluent open, we can go ahead and start the general setup of our simulation. For solver type, we are going to want to keep this to pressure based. Absolute is fine. Here we're going to want to change the time to transient because we want to see the von Karman effect in this simulation, and von Karman effect is a transient effect, and we're going to keep this to 2D planar, so that is all good to go. For the model type, we are going to change this to viscous laminar. So we're going to double click on viscous here, and it's going to bring up this window like so, and we're going to press on laminar. We're going to press OK. Now, the next thing that we're going to want to do is specify the material for our simulation. So we can go ahead and press on the plus here and press beside fluid. And as you can see, by default, it has air. So by default, ANSYS is going to give us air as our material, but we want to use water instead. So what we can do is double click on air to open up this window. And as you can see, for air, ANSYS already has these properties for the constants. But again, we're going to use water. So we're going to press on Fluent Database. And this is going to open up the materials database, and we can scroll all the way down to go find the liquid water right here. As you can see, this lists all of the water properties that ANSYS has by default. And so to add it to our project, we'll go ahead and press on copy. And we're going to close this window and close this one too. So now we can see in our tree that water liquid has been added as a fluid material to our project. Now, this doesn't mean that the domain is actually liquid water now, because by default it was air. So we need to make sure that ANSYS is going to use liquid instead of air. So we're going to press on cell zone conditions and press on FFF_surface. And as you can see here, the material name is air and not water, because by default, again, ANSYS was going to use air. So we can press on the tree here and change this to liquid water. Now, if you had more materials listed or added more materials to your project, they would all be under this list here. And we can go ahead and press on apply to actually apply this to the program and close the window here. Now we're going to specify the boundary conditions for our project. So we can go ahead and press on boundary conditions. And as you can see here, this is where all of our name selections are that we did in the mesher. So it's important to name different aspects of your geometry in the mesher in order for Fluent to understand how to apply certain boundary conditions. And we can check these boundary conditions too. If we go ahead and press on cylinder here, we can see that the type is a wall, so that is good. For the inlet, it's a velocity inlet, so we're going to specify the velocity later. For outlet, it's a pressure outlet, so that is good. And the wall, evidently type wall, so that is good as well. Now we're going to specify the velocity magnitude of the inlet, so we're going to double click on inlet. And this is going to open up this window here, and as you can see, we can specify the velocity magnitude here. So I'm going to put as a velocity magnitude 0.0001. And the reason why I'm putting this velocity magnitude is because it's going to give me a Reynolds number of 100 based on the other constants that were predefined in ANSYS, such as the density, the viscosity, and we specified the diameter of our cylinder to be 1 meter. So now with our velocity added, we can go ahead and press apply to apply this to the velocity inlet, and we can close this window. So now we have a velocity of 0.0001 meters per second applied to the inlet. We are now going to double click on reference values, and we are going to take the reference values from the inlet. So if we choose inlet from the tree here, you can see that it adds the values for the fluid, the velocity, the density, and the viscosity, all to the reference value tree here. For solution methods, we are going to double click on methods, and down here, we are going to change this to second order implicit. Now we're going to add the monitors for our solution. So we can go ahead and double click on report file here, press on new, and press on new over here, and go down to force report and add drag. So now what we're doing is we're creating a drag report for our simulation. This is going to open up this window here. We can rename this to drag. The drag coefficient is what we want to find, and we want to calculate the drag over the cylinder wall, so that is good. Click on that. And for force vector is good, 1 in the x and 0 in the y, because we know that the drag is going to be in the x direction. And we're going to press on print to console down here. Press on OK. We're going to also want to calculate the lift as a solution for our simulation. So we're going to add a lift plot as well, similar to the drag. We're going to go down here, but we're going to choose lift instead of drag. And we're going to rename this to lift to note that this is our lift monitor. Lift coefficient is good. Apply it to the cylinder wall. For the force vector, we know that lift is perpendicular to drag. So it's good that the vector is 1 in the y and 0 in the x. And we're going to go down here and print this to the console. And what print to console does is it's going to print in real time the graphs in our console here while the calculations are being run. We can go ahead and press on OK down here, press on OK here, and close this window. So now we can see that we have 2 report files, one for our drag and also one for our lift. And if we go ahead and press on the plus beside report plots, we see that we have a plot for drag and a plot for lift as well. Next, we're going to press on initialization, and we are going to use hybrid initialization. So press on that and press initialize. And as you can see down in the console window, we see hybrid initialization is done. So that is good to go. And the next thing that we're going to want to do is press on calculation activities. And as you can see here, we have a field called autosave every time step. And so we're going to put a 1 here instead of a 0 so that we save the time step of every calculation, and we can send this to the processor later on in order to create an animation. Now this is going to generate quite a bit of data. So if we're running this simulation for a lot of time steps like we're going to be doing for this one, it would be wise to put either every 5 time steps or every 10 time steps, because there's not going to be a big difference between each time step. But if data is not a problem for you and you have a lot of storage space, you could put 1 here to save every time step of the calculation. Now we can finally go ahead and run our calculations for the simulation. So we can press on run calculation, and we have to define a few more parameters before we can start. The first one is the time step size. Now, a good rule of thumb for the time step size for CFD simulations is to make it so that it takes a time step at least at the boundary of every smallest element in your mesh. And so what do I mean by this? Well, we specified our smallest element to be 0.025 meters during the meshing stage, and we know that the velocity of our fluid, because we specified that as well, to be 0.0001 meters per second. So if we divide the size of the smallest element in the mesh by the velocity, we get that it will take 250 seconds for the fluid to move across that smallest element. Therefore, it would be good to specify the size of the time step to be at maximum 250 so that we can take a time step at least at the boundary of every smallest element, or make it less than 250 in order to take a time step in between the smallest elements. If we were to make it larger than 250, then we would be skipping elements in our mesh, and this may lead to an inaccurate result during the CFD calculations. So for the simulation, I'm going to put the size of my time step to be 250 seconds. And we're going to run this for 4,000 time steps. And the reason why this number is so large is because we want to see the full transient time of the von Karman effect. During the calculations, we're going to see the lift and drag plots. And in the lift plot specifically, we're going to be seeing oscillations up and down when the von Karman effect is taking place. Now, over time, these oscillations are going to grow and grow in amplitude until a certain point at which they will stabilize. So we want to see that full transition period from when the oscillations are very small to the point where they're very large, but they've become stable at that point. And we're going to change the max iterations to 40 instead of 20. So now with all these parameters put into place, we can go ahead and run our calculation. And we can go ahead and press on calculate. And now we can see that it is printing all the results to the console, and it's opening up quite a few tabs for our lift and drag plot. So as mentioned before, it is now printing the lift and drag in real time as it's running the results. And since we are running this for 4,000 time steps, it is going to take a bit of time. So I will cut back to you guys when it is done. Welcome back, guys. The calculation is now complete. When it is complete, we will get a message that appears like this that says calculation complete. So we can go ahead and press OK on that. We can go ahead now and check our results. So if we press on the lift plot tab here, we can now see our coefficient of lift over time plot for our simulation. As you can see, the results are fairly good. The oscillations at the beginning are fairly small, where the von Karman effect hasn't really taken too much of an effect yet on the flow. But as time progresses, the amplitude of the oscillations get bigger and bigger as the von Karman effect is starting to be more dominant, and the amplitude of the oscillations keeps on getting bigger up until a certain point at which they plateau, and this is where the solution sort of stabilizes. We can also go take a look at our drag plot. We can see at the beginning that it shoots up to a really high value at first, but then sort of stabilizes at the lower values of the time. We can see back in the coefficient of lift that the von Karman effect really started to take effect around 300,000 seconds. And if we go back to the drag plot, this is where the plot sort of peaks up a little bit and then starts to oscillate. These details are very small in this graph simply because the graph did shoot up at a really high number at the very beginning. Now, we could see these details a lot more clearly if we were to adjust the scale on the y-axis of this plot. So now we can go to the post-processor in order to view the contours, streamlines, and the animation that we've created. So we can go back to the workbench by clicking the big X at the top. And now that we are back in Workbench, we can go ahead and double click on results to start the post-processor. Now with the post-processor open, we can go ahead and start making our contour plots and streamline plots. So first we're going to press on the Z-axis here in order to make our model planar to the screen. Now in order to make the contour plot, we'll go ahead and press on the rainbow icon up here. Contour run, press OK. For the domain of our contour, we're going to select the FFF_surface, which is the surface of our geometry. We'll change the location to symmetry 1. And we'll take a look at the variable of velocity in the U direction. And by doing this, we'll be able to see how the flow accelerates as it goes around the cylinder. Now, if we wanted to take a look at a different variable for our contour. We could also select pressure, for example, which would give the pressure at every location as the flow goes around the cylinder as well. So we could go ahead and choose any variable that we would want. But for this particular contour, we'll go ahead and look at the velocity in the U direction. Now, in order to make a smoother gradient in the colors for our contour, we can up the number of contours here to 100 and press apply. So now we're able to see the contour for our velocity gradient of our fluid flow. We'll actually go ahead and deselect wireframe so that we can see the contour more clearly. From the contour, we're able to see the von Karman effect very clearly. We can see at the trailing edge of the cylinder, there are a lot of vortices that are shedding off of it. Now, the gradient is still a little choppy, so what we can do is we can up the number of contours to 200 to make it an even more gradual gradient in colors. I should also note that the time step that we're seeing right now is the last time step. So if I go ahead and press on the time step selector up here, the little clock icon, this brings up all of the time steps that we saved from the solver calculations. So as you can see, we have 4,000 time steps and is in fact showing the last one. If we scroll up here and choose a different time step, if we click on the time step and press apply, we can see that our contour is going to change to that more current time step. So as you can see, the von Karman effect has changed from the 4,000 time step to the approximately 2,000 time step. And if we go even closer to the beginning, we can see that the von Karman effect is going to change even less. So this is where the amplitudes of the lift graph were a lot less because the von Karman effect or the shedding of the vortices weren't as dominant. We'll go ahead and change this back to the 4,000th time step for the time being. So now we'll go ahead and create our streamline plots. First, we're going to deselect the contour in the tree up here. And as you can note, nothing is going to appear on our console because we have the wireframe also unchecked. So if we check the wireframe, we'll be able to see the wireframe of our model. In order to start the streamline plot, we're going to go ahead and press on the airfoil icon at the top, right beside the rainbow icon that we pressed on before. Streamline 1 is okay. Now the procedure for making the streamlines is going to be very similar to the contours. For the domains, we're going to put the surface again. We are going to start the streamlines from the inlet. They'll be equally spaced, and the number of points here is going to determine, much like how many contours we have, it's going to determine how many streamlines we're going to have. So the more points or the more start points we have for streamlines, evidently the more streamlines we're going to have and the more full our graphic is going to be. So we can go ahead and change this to 100 to get 100 streamlines. For the velocity, for the variable, sorry, we're going to keep this to velocity, and we'll go ahead and press on apply. And that is our streamline plot for the velocity gradient, which encompasses, again, the von Karman effect, as that is what we were looking for while doing this simulation. And much like before, if we press on the clock again, the time step selector, we could go ahead and change which time step we're looking at in our console view window here. Now we can go ahead and start our animation. So in order to do that, we're going to close this window here. And we're going to make the animation out of the contours instead of the streamlines. So we're going to go ahead and press on the contour and unselect the streamline and wireframe. In order to make the animation, we're going to press on the little film icon here beside the clock. For the type of animation, we're going to keep this as a time step animation because that is the information that we have. We'll drag this counter all the way to the beginning in order to start at our time step number 1. Evidently, this animation is going to be controlled by our time steps because that is the information that we solved in the setup of the program. And if we wanted to, we could specify the range of the animation that we want. Like I mentioned before, we generated so many time steps and so many data for this simulation, and it would have been fine to save every 5, 10, or even 50 time steps in order to make this animation a little shorter, because the difference between the first time step and the second time step, for me, the fluid's not moving very quickly, so there isn't going to be much of a difference between time steps for the simulation. For the advanced frame selection controls, we could go ahead here and press on the tree if we want to specify a certain type of time step to be chosen within the range of our animation. For the number of repeats, we're going to keep this to 1. Now, if you wanted to make, say, a GIF or something that repeats many times, you could put the number of repeats for this animation that you want, and it's going to put it all in one video file for you. Now, to actually save the movie to our computer, we're going to go ahead and press on the box beside Save Movie. And as you can see, the box here describes where the file is going to be located on our computer. And we can go ahead and change the FFF. That will be the file name of the movie. And if we wanted to change the location, of course, we could open the little folder icon here and change where it's going to be stored. Now, to actually start creating the animation, we're going to go ahead and press on the little play icon here. As you can see down in the bottom here, we have a progression bar that appears, and it says which time step it is loading. So as it runs through the animation, creating each frame and splicing all these frames together to create the animation, it is going to tell us which time step it's at, and it's also going to display the time step to the screen. Now, since the change in between our time steps is so small because we saved each time step during the solution, we're not going to see many changes right now because it's going to take quite a long time for the animation to be created. That being said, I'm going to cut until the animation is complete, and the next frame I'm going to show you is the completed animation on screen. Welcome back, guys. So as you can see, I now have the created animation on my screen right now. So I can go ahead and press on play to view the animation. And this turned out to be quite the lengthy animation, I must say. It turned into a 2-minute and 45-second animation, which is pretty long. If we wanted to make this shorter, again, we would probably save less time steps in between so that we see the change happen more rapidly. The other thing that we could obviously do is reduce the range of our animation. But this is a pretty cool animation to watch because we can see it right from the beginning, where the von Karman effect is not taking place. There's not much happening. And we are naturally seeing slowly the progression of the vortices starting to shed from our cylinder. So I hope this tutorial was helpful for you guys in order to do the fluid flow around a circular cylinder in order to see the von Karman effect that is slowly starting to appear on the screen right now. In the next episode, we're actually going to go over the steps to do the von Karman effect for 2 cylinders in tandem with each other, and we're going to compare the results between the 1-cylinder results that we have now and the 2-cylinder results that we're going to obtain in the next episode. Now, the 2-cylinder tutorial, in order to see the von Karman effect and the fluid flow, is going to be much quicker, obviously, because many of the steps are the same as the 1-cylinder results, but I'm still going to go through the steps quickly in order to go through it again with you guys. So that is it for me for this tutorial of the 1D cylinder and the von Karman effect. I hope you guys found it very helpful. Don't forget to leave a like on the video, comment if you have any questions, and don't forget to subscribe for more engineering content like this.